before the first light patterns whisper in the dark. From a trembling vacuum to the cosmic web, from the first stars to the birth of oceans and mines, this film traces how everything may have risen from almost nothing. Anchored by real observations, ancient afterglow maps, galaxy surveys, meteorites and ocean worlds, it moves in a calm arc, data anomaly, mystery speculation. Settle in, breathe slowly, and follow the night. If the wonder resonates, please like this video, subscribe for more, and ring the bell to journey deeper with us. In the hush before light, the universe exists as a hot and crowded possibility, a sea of energy changing faster than any clock can track, and yet it already carries the seeds of pattern that will outlast stars. In the first instant, temperatures soar beyond the reach of furnaces, and the familiar identities of matter do not yet exist. There are only fields and quanta sharing energy in restless exchange. As expansion begins, that energy thins and cools, and with cooling comes the first decisions. What counts as a particle? What counts as a force? What will be stable, and what will fall apart almost as soon as it forms? In this beginning, simplicity reigns, but it is not the calm simplicity of a blank page. It is a pressure that forces outcomes, narrowing the future into channels of possibility. Within the first heartbeat of cosmic time, a soup of light and the raw ingredients of matter flows without resistance, and the notion of a boundary has no meaning because space itself is the thing that stretches. The earliest narrative leaves almost no direct evidence, yet it is not lost. It is written into later fossils that appear when the universe finally becomes transparent to light hundreds of thousands of years after this initial storm. Those fossils are tiny variations in temperature, delicate freckles that missions from Earth will map in the far future, but which form now as slight differences in density that tug a little harder here and a little less there. The physics is unadorned where there is a little more stuff. Gravity pulls a little more, and so the difference grows. Where there is a little less, gravity relents and emptiness becomes a little wider. This logic seems inevitable, but it needs a starting template, a first set of unevenness, and the question of how that template appears becomes the first deep riddle. The overall story follows what instruments will later confirm the universe cools as it expands. Within the first few minutes, protons and neutrons settle into simple nuclei. After hundreds of thousands of years, electrons and nuclei combine to form neutral atoms and light goes free. These statements are as secure as any in cosmology, because they are anchored by observed ratios of elements and by the sky-filling glow of the ancient microwave afterglow, but they do not explain why the first state is so special. The universe begins astonishingly smooth and astonishingly flat on large scales, meaning space does not curve in on itself, or bend conspicuously outward, and points separated by more distance than light can bridge still share the same temperature to a remarkable precision. Known physics has no simple reason why regions that have never communicated would coordinate so closely. This is the horizon puzzle, a calm surface concealing a storm of implication. The flatness of space is another quiet astonishment. If the curvature ever differed strongly from zero gravity, would have already steered the whole into an early collapse or a runaway thinning. Yet observations show a balance that holds across distances measured in billions of light years. These balances do not feel accidental, and that unease fuels the search for a mechanism that smooths, flattens, and seeds all at once. Before that mechanism is named, the data already push toward it. When satellites funded by agencies like the National Aeronautics and Space Administration and the European Space Agency eventually fly, their maps reveal temperature variations of only a few parts in 100,000 across the ancient sky, and those variations line up in a specific pattern of sizes and strengths that match a universe born with a simple recipe, begin extremely hot, expand cool, and let gravity and pressure trade influence like alternating beats in a drum. The pattern is not random. It favours certain angular scales as if the young cosmos carries a chord progression set by its own density and sound speed. The ancient universe is not silent. It rings with pressure, waves ripples of compression and rarefaction in the plasma of light and charged particles, and when atoms finally form and light decouples, that ringing freezes into a textured photograph. The photo shows that the early cosmos is both uniform and imperfect, a balance that makes structure possible. Absolute smoothness would drift forever into nothing but featureless haze. Excessive clumpiness would collapse into black holes before stars have a chance to form. The observable universe chooses the narrow middle, and the odds of landing there by chance seem small, which returns the story to the tension between inevitability and design. Nothing in the later behaviour of matter explains the special initial conditions. The arrow of explanation still points backward. Another clue lies hidden in the inventory of matter and light. The early fireball contains slightly more matter than antimatter, a tiny asymmetry that allows any atoms to remain after mutual annihilation. That tiny preference shapes everything that follows galaxies, stars, planets, and the narrator telling this tale. The physics behind that preference is not fully settled. Experiments on Earth discover small imbalances in the behaviour of particles and their mirror twins, but those measured effects seem too weak to account for the cosmic surplus. The beginning therefore holds at least 3 surprises: the coordination of temperatures across unreachable distances, the suspicious flatness of space, and the slight tilt toward matter over antimatter. Each points to processes that run faster and deeper than ordinary thermal history, and the way those processes act leaves behind the faint template that later observations will confirm. To frame these surprises without resorting to untestable myth, the narrative leans on models that stretch and amplify the tiniest fluctuations, turning the restless tremor of empty space into the architecture of the future. In that view, vacuum is not nothing. Vacuum is a medium whose energy can change and whose state can drive space to grow at a pace that outruns any signal. Such growth would wipe away curvature and knit far apart regions into a shared condition, before they separate, handing the horizon puzzle a practical solution and flattening the geometry as a side effect. It would also stretch quantum jitters into macroscopic seeds that gravity later fattens into galaxies. The evidence for such a phase is circumstantial but coherent, and it sets the stage for a hunt that continues in the polarization patterns of the ancient afterglow, and in the distribution of galaxies across space. In the meantime, the most conservative reading of the first lightless era remains compelling in its restraint. The universe begins hot, dense, and almost uniform. It cools as it expands. Subtle irregularities grow into everything visible. Yet even this sober arc points toward a deeper question that has not gone away. If the origin is a state rather than an event, what selects that state, and what selects the rule by which space and time evolve from it? If the origin is an event, what stands before it, and can before even be a meaningful word when time itself is part of what is coming into being? Observations show the fingerprints of a process, and the process appears lawful, but the law is not a cause in the ordinary sense. The stage is set without lamps, and still the scenery knows where to stand. Guidance arrives in the least likely place, in patterns laid down before light could move freely, patterns that will steer the first stars, the first galaxies, and the quiet emergence of islands, where chemistry and heat write stories on rock and sea. The beginning does not answer the ultimate why, but it narrows the possibilities of how, and as instruments grow more sensitive, they keep returning the same message from the night. The map that names the later world is drawn before light, and every later flare is an echo of those first decisions preserved in a sky that still glows with its own memory. The first detailed map of the ancient sky arrives long after the light itself has been travelling, and yet it reads like a weather report from the childhood of space. The cosmic microwave background, the faint afterglow left when the universe first became transparent, spreads across the whole sky as a nearly perfect bath of light about 3 degrees above absolute zero. It carries small temperature variations only a few parts in 100,000, and those tiny variations arrange themselves into a pattern that reveals how matter and light competed before atoms formed. Early satellites built under the National Aeronautics and Space Administration and the European Space Agency trace this pattern with growing clarity. The Planck mission later cools its detectors and watches from a quiet gravitational harbour far from the Earth, and it turns the sky into a chart where statistics stand in for eyewitnesses. In this chart, the size of the hottest and coldest spots is not random. It prefers certain angular scales because the young universe is a resonant medium. Before atoms exist, light and charged matter lock together into a fluid that behaves like a drum skin stretched across all of space. Pressure pushes out, gravity pulls in, and the two trade strength in rhythmic fashion. At the instant when electrons finally bind to nuclei and the fog clears, those waves freeze. The cosmic microwave background remembers their phases. Investigators turn the sky into numbers by counting how strong the variations are at each angular size. The resulting curve shows peaks and valleys like a musical score. The first peak marks regions that had time to squeeze once. The next peak marks regions that had time to squeeze and rebound. Further peaks track higher harmonics. The heights and positions of these peaks become rulers for the contents of the universe. More ordinary matter raises some peaks and lowers others, because additional mass makes gravity's pull stronger, while adding inertia to the fluid. The amount of unseen dark matter sets the overall depth of the gravitational wells. The curvature of space shifts the apparent sizes of all features. When the analysis is complete, the map says the large-scale geometry is astonishingly flat. The inventory of matter is dominated by the unseen kind, and the rest of the energy budget hides in the very fabric of space as a slow push that accelerates expansion. The cosmic microwave background also carries polarization, a faint pattern in the way the light's electric field is oriented. This polarization arises because the last scattering of a light off free electrons in the fog of the early universe is not perfectly symmetrical. The ripples are easily made by the acoustic waves that already sculpt the temperature map. The whirls would signal gravitational waves present when the fog cleared, possibly stretched from the smallest scales by an early burst of expansion. The Planck maps show that dust in our own galaxy can mimic the world pattern and must be carefully removed. So far, the ancient sky remains quiet on primordial whirls, but the search continues because a detection would point directly to physics that no particle collider can reach. The map is more than a description of what once was. It links to the present-day universe through the way sound waves leave imprints in the distribution of galaxies. Where there was a preferred separation between hot and cold in the afterglow, there is a preferred spacing between clusters in deep surveys today. This fossil ring acts as a yardstick for cosmic distances, and combined with supernova measurements confirms that the expansion of the universe speeds up over time. Even a perfect map can surprise in quieter ways. On the largest angular scale, some alignments look a little too tidy, as if the lowest notes in the cosmic score prefer a direction. A wide and unusually cold region nicknamed a spot draws attention, because chance can make such a feature, but not often. Foregrounds of dust and gas complicate the evaluation, and careful cleaning reduces some of the tension, yet a residue of curiosity remains. These anomalies do not break the standard picture, but they keep the door open to the thought that the early conditions might have carried asymmetries invisible to simpler models. When cosmologists infer the current expansion rate by interpreting the ancient afterglow with the standard model, they arrive at a number that is somewhat lower than measurements that build a ladder of distances from nearby stars to faraway supernova. The difference is not enormous, but it is persistent across different teams and methods. Either one side misreads its data, or the underlying model misses a small ingredient that nudges the early and late universe to different answers. Here the first map acts like a referee who also whispers a riddle. The accomplishment is severe and elegant. Detectors of astonishing sensitivity must stare at the sky while shielding themselves from the earth, the sun, and their own warmth. Satellites scan again and again so that random noise averages away, leaving the common signal. They compare their results with independent measurements from galaxy clustering and from the light of distant explosions. The result is a map that turns the universe into a solved system, with a few unknowns highlighted in red ink. If the geometry is so flat, by what process did it become so? If the temperature patterns are seeded by fluctuations in fields that pervade space, what is the field that dominated the earliest moment? The search for gravitational wave imprints in polarization continues because those imprints would speak for an early engine that left only echoes. It shows that the hiss of the oldest light can be converted into a list of numbers that predict where galaxies prefer to assemble and how fast space itself pulls them apart. It says that an infant cosmos still a fog already knows the outlines of its adult face, yet the map stops at the surface where light went free. Beyond that surface lies an earlier domain where theory guides and data hint. The first map therefore serves both as a foundation and as a veil. It fixes the stage for the next act while refusing to show the actor who set it. By turning ancient heat into a modern chart, it narrows the routes that might lead from nothing to everything, and it leaves the viewer staring at a sky that is both familiar and impossible, a sky that says here is how, and then just as steadily asks again why. Vacuum looks like nothing yet. Modern physics treats it as a restless medium that never quite sits still, and the early universe turns that restlessness into a visible scaffold. A quantum field is defined as a spread-out entity that fills all of space. Particles are ripples on this field, and even when no particle is present, the field still carries energy. The lowest energy arrangement is called the vacuum state, but calling it empty obscures what truly happens, the vacuum jitters. For fleeting moments, pairs of excitations rise from the background and then sink back, a churn so brief that no single event can be caught, yet the whole sea leaves measurable marks. In laboratories, metal plates held very close together feel a slight push toward each other, because the allowed ripples between them are filtered compared with the ripples outside. This tiny attraction, known from meticulous bench experiments, is one of several quiet proofs that so-called emptiness has structure. Other traces show up when electrons bound within atoms shift their energy by a minute amount, altering the color of light they absorb and emit in ways that can be accounted for only if the vacuum itself shakes their dance. These details are small, yet they say that nothingness is a misreading. If even the quietest background carries energy, then the early universe packed into a hotter and denser state must have felt the influence of vacuum energy more strongly than today. The suggestion is that a particular field could have temporarily dominated, pouring almost constant energy into space and driving expansion, at a pace that outstrips any signal. Such a phase would smooth away curvature and stretch any initial patch into an enormous, nearly flat domain, while also enlarging the tiniest fluctuations into seeds that gravity later fattens into galaxies and clusters. This proposal, often called an inflationary episode, links the quantum restlessness of the vacuum to the largest patterns mapped in the ancient afterglow of light. The data align in remarkable ways. The temperature speckles in the sky later charted by space missions under the National Aeronautics and Space Administration and the European Space Agency look statistically like the stretched imprint of quantum noise, nearly the same on every scale, with a slight tilt away from perfect balance. The distribution of galaxies seen in wide surveys carries an echo of sound waves frozen when atoms first formed, and the preferred spacing seen in that fossil ring matches the predictions of a universe that begins nearly flat. These anchors make the picture persuasive, but they do not end the questions because fields are many and choices are few. What kind of field drove the early burst? How did it switch off? And what fixed the level of its energy? Each version of the story tries to answer by writing a potential landscape for a field to roll across, but the freedom of that writing warns against overconfidence. A separate clue arrives from a different direction. In 2019, a collider experiment confirmed that the Higgs field, a particular quantum field whose average value fills space and gives many particles their mass, exists as a pervasive background. That discovery is not directly responsible for the early burst, yet it strengthens the habit of thought that treats fields as the true constituents with particles as their excitations and vacuum as a material state. If vacuum is a material state, then its energy should gravitate. General relativity says that any energy density, even that of empty space, bends the shape of space and time. Astronomers see a slow push that accelerates the cosmic expansion in the present era, a phenomenon labeled dark energy. The simplest reading of this push is that space contains a small but non-zero vacuum energy. However, when theorists try to calculate the size of vacuum energy by adding up the expected jitters of all fields, the answer overshoots the observed value by an absurd factor. The disagreement is not by 2 or by 10. It is by many orders of magnitude, a gulf so wide that words struggle to convey it. Here the vacuum reveals itself as a double-edged guide. It seems to explain a great deal about the smoothing and seeding of the early universe, and perhaps about the present acceleration, yet our understanding of its scale is shockingly poor. The early universe may exploit a temporary state, a plateau, in a field's energy to drive its sprint and then exit to a lower energy condition that allows ordinary hot expansion to proceed. That exit must not shatter the smoothness it just created, and must not leave a residue of exotic relics that would be obvious today. The hurdles are demanding, but they make the narrative falsifiable, and that is a strength. Observers search for indirect fingerprints of the early vacuum dynamics in the polarization of the ancient afterglow. A specific swirling pattern would indicate that space itself rang with gravitational waves during the sprint. Thus far, the sky has yielded no decisive swirl beyond what local dust and magnetic fields can produce, and the field remains in suspense. The absence of a clear signal does not kill the idea, but it trims possibilities and nudges model builders toward gentler versions. Closer to home, the uneasy arithmetic of vacuum energy persists. Why should the vacuum energy be so small today, when every naive calculation makes it so large? Perhaps there is an unknown symmetry that cancels most of it. Or perhaps what we call vacuum energy is not a fixed property at all, but the effect of a new field slowly changing over cosmic time, Or perhaps there are many patches of space with different vacuum energies, and observers arise only where the value permits a long-lived universe of stars and chemistry. Each possibility invites a test, and each test is hard. Telescopes stretch to measure the expansion history with greater precision. Dedicated surveys count galaxies by the millions to see whether growth appears slightly slower or faster than expected. Detectors deep underground listen for the quiet clink of dark matter particles that might also speak to the structure of the vacuum. The most striking aspect of this entire line of thought is how it bridges extremes. From the tiny shift of an atomic line in a laboratory to the great sweep of a sky-wide map, the same concept of restless vacuum ties caused a consequence. An experimenter nudges metal plates together and watches them creep. A satellite stares at the cold afterglow and sees a pattern of spots. A theorist writes a potential curve that would let a field linger high and then fall low. A collider shows that at least one field indeed fills space even when no quanta dance upon it. Each strand reinforces the others without closing the loop. The vacuum is busy but mysterious. It appears simple, but hides bookkeeping we cannot finish. If creation requires no raw material beyond a stage and laws, then a stage made of fields with intrinsic energy could in principle light its own fire and then step back. Yet even that inviting simplicity slips into new questions. What sets the initial state of the field that drives the sprint? What decides the exit? Why do the leftover vibrations seed just the right amplitude of clumpiness, small enough that space does not collapse early, large enough that stars and galaxies form on schedule? Why is the vacuum energy that dominates today so tiny compared with almost any calculation? These are not rhetorical spirals, they are provocations. They keep instruments pointed outward and theory pointed inward, and they sharpen the deeper theme of this story. Nothing is not nothing. It is a fabric whose weave becomes visible when stretched across cosmic distances, and audible when struck by the hot plasma of the first light. The universe that looks empty speaks in the pressure of plates, in the hum of atoms, in the quiet push of acceleration, and in the mottled memory of the ancient sky. Out of that hum grows a scaffold on which structure assembles a scaffold that tells us that becoming can begin from the tremble of the ground itself, even as the ground continues to conceal how and why it trembles at all. The idea of an early burst of expansion enters as a remedy for unease and stays because it matches what the sky records. If space swells by an enormous factor in a blink of primordial time, then any initial curvature is ironed almost flat regions that would otherwise never speak come into thermal contact before they drift apart, and the tiniest jitters of a field are stretched into the scaffolding that gravity later builds upon. This sprint is not motion through space, but the growth of space itself, an exponential swelling that outruns any signal and wipes away prior clutter, while preserving faint memory in frozen patterns. In this picture, a single field lingers high on a plateau of energy, so that the fabric accelerates rather than slows. While it lingers, the field's fluctuations appear as small hills and hollows in the energy density, and the swelling magnifies them from subatomic scales to sizes larger than galaxies, leaving a nearly scale-free spectrum, with a slight tilt that favours broader waves. When the field finally rolls off its perch, its stored energy decays into a hot bath of particles, and light and ordinary expansion resumes with initial conditions already smoothed and imprinted. The appeal is that one mechanism addresses several puzzles at once, yet its worth rests on tests. The ancient afterglow provides the most direct judge. It shows temperature variations of about 1 part in 100,000 arranged, so that larger waves carry slightly more power than a perfectly balanced spectrum would allow, just as a long but not infinite sprint would create. The map's peaks and valleys match the expectation of a universe that begins nearly flat and then cools into a plasma that rings before atoms form. The tilt differs gently from a perfect balance by a few percent in the direction predicted by a field rolling slowly. The absence of strong departures from a near Gaussian speckle pattern also limits how wild the engine can be. These simple-sounding statements close many doors and make inflation less a license to imagine anything than a sieve that throws out most possibilities. Even so, the central claim seeks a decisive relic that would be hard to forge by other means, a background of gravitational waves set loose during the sprint, leaving a faint curling pattern in the polarization of the afterglow. Experiments have pursued this twist for years, scanning the cold sky from dry high ground and from near space. The signal, if present, would be tiny and easy to confuse with dust grains in the Milky Way that align with magnetic fields and polarize light. An early claim of detection faded when such dust was measured more fully. Since then, teams have combined data sets, mapped galactic foregrounds with patience, and lowered the upper limits on the strength of the primordial waves. Each non-detection trims the parameter space, telling theorists how gently the field must have rolled, and how low the energy scale might have been. Another test hides in the distribution of matter. Inflation predicts that fluctuations begin in a nearly single clock fashion, in which all components are perturbed in lockstep. Large departures would produce isocurvature patterns where some species fluctuate against others, but current data from the afterglow and from galaxy surveys show no strong trace of that mismatch. The young cosmos also lacks the heavy relics that some models would overproduce another indirect nudge toward a simple engine. The strengths are real, yet sharp questions remain. What field drove the sprint? Why did it sit high long enough and then exit so neatly? How did it avoid leaving scars in the form of topological defects or awkward inhomogeneities? If the mechanism is generic, does it run only once? Or does it spawn a mosaic of regions with different low-energy properties, some fertile for long-lived chemistry and some not? Such a mosaic is sometimes called a multiverse here, a pragmatic possibility rather than a boast. If the engine is fed by a landscape of many plateaus, then pockets of space could settle into different valleys, each with its own constants and particle content. Observers would arise only where conditions allow a long era of stars. This shifts explanatory weight rather than removing it, and remains controversial because it offers fewer crisp tests, yet even here not everything is beyond reach. One can search for scars from collisions between neighbouring pockets or for delicate statistical skewness in the ancient map that would hint at extra fields involved during the sprint. No such signs have been found. Alternatives compete. Some imagine a slow contraction that rebounds, or an era where effective light speed runs higher, or a network of strings whose vibrations structure space. Each must match the same anchors and then offer something extra. So far, inflation remains the simplest tale that fits all the main data while leaving room for refinement. Even within that tale, the details matter. Model builders catalogue potentials with slopes and plateaus of many shapes, because the exact linger and exit change. The predicted tilt, the strength of primordial waves, and any subtle non-Gaussian fingerprints. Some versions fit better than others under the latest limits. The next generation of polarization maps may push sensitivity to the level where a gentle background of gravitational waves would finally appear, or be constrained below a natural threshold for many common shapes. The temptation is to declare the sprint both inevitable and explanatory, yet the narrative resists closure. A mechanism can flatten seed and link far regions, but it still requires a starting position and a way to end. It might be that the very questions lose meaning if time itself emerges from a prior pattern, where before and after are not yet defined. Or it might be that the laws permit many openings, and we inhabit one that allows a long stretch of order. For now the measured sky writes down constraints, and the early breath remains an inference that has weathered many attempts at falsification. It has the marks of a good guide in science. It makes specific predictions. It connects the smallest known scales to the largest, and it invites failure by asking for evidence that could undo it. In the hush between first fog and first light, the breath that may have started everything leaves only whispers. The whispers are enough to draw maps, build instruments, and turn suspicion into expectation, not enough to answer why the breath began, yet sufficient to keep the search precise and brave. From the first ripples to the present tapestry, gravity turns slight unevenness into a cosmic web, a lattice of filaments and clusters surrounding broad empty basins where little forms. In this growth, the rule is direct over dense regions pull harder, and gather more under dense regions surrender matter to their neighbours and inflate into voids. The unseen majority dark matter that does not feel light or ordinary pressure collapses first because it streams freely and radiates no heat. It settles into halos whose overlapping skirts connect into long strands. Gas traces this invisible skeleton slowed by shocks and its own pressure. Where the scaffold knots most tightly, gas cools, condenses and ignites into stars that announce the hidden architecture. Numerical experiments start with the measured pattern of early fluctuations and let the equations of gravity run. They produce a network that resembles what deep surveys later reveal, with bridges stretching for hundreds of millions of light years and intersections swollen into clusters that bind together thousands of galaxies. On the ground, the Sloan Digital Sky Survey and its successors chart positions and distances for galaxies by the million, sketching the same filamentary foam first predicted in computers. A gentle excess of galaxy pairs at a preferred separation, the fossil of sound waves imprinted before atoms formed, appears in these maps as a standard ruler that ties the web to the ancient afterglow and anchors distance. Further confirmation arrives when weak gravitational lensing, the slight coherent distortion of galaxy shapes by intervening mass, draws a shadow map of the invisible structure. By stacking millions of shapes, the Dark Energy Survey and other campaigns reconstruct sheets and threads of mass, and their statistics match those from the temperature ripples frozen into the sky long ago. Light at specific wavelengths cuts a different path through the same maze. In spectra of distant quasars, a forest of delicate absorption lines marks cool hydrogen drifting between galaxies. The spacing and strength of these lines track the rise of structure and the temperature history of the intergalactic medium as filaments condense and voids open. At the nodes of this network, clusters become laboratories where several physical streams meet. They trap oceans of hot gas that shines in high energy, light bend light into arcs that expose their total mass, and scorch in flowing material with shocks and turbulence. Collisions between clusters like the well-known bullet-shaped encounter split the luminous gas from the dark mass and show that most of the gravitating matter is not ordinary. Across this scaffold, feedback acts as a thermostat. Explosions from massive stars and outflows from central black holes pump energy back into their surroundings, limiting the pace of star formation and preventing gas from condensing too quickly. Simulations that add these ingredients reproduce observed counts, colours and sizes of galaxies more faithfully than gravity alone, which would make too many small dense systems too early. Yet the web still carries riddles that point beyond a simple picture. Satellite galaxies around some large hosts lie in thin, rotating planes more orderly than a random assembly would suggest. Their existence may be a quirk of small number statistics, a sign of anisotropic accretion along filaments, or a clue that interactions in the unseen sector matter in subtle ways. In the smallest galaxies, measured inner mass profiles appear flatter. The naive collapse would predict the long-discussed core and cusp tension that might be eased by repeated heating from bursts of star formation, or by dark matter that scatters with itself. Counts of the most massive subhalos around Milky Way-sized systems once seemed too large for the number of bright companions, observed a challenge described as too big to fail. Careful accounting, updated distances, and the throttling effect of feedback have softened but not erased the question. On larger scales, the growth rate inferred from peculiar motions and weak lensing sometimes sits slightly low compared with expectations tuned to the ancient sky, a small but persistent mismatch that encourages more precise surveys and invites models in which the unseen component is not perfectly cold or perfectly simple. The geometry of the web also shapes how galaxies spin and feed. Orientations and angular momenta correlate weakly with nearby filaments, as if tidal torques from the surrounding structure taught forming disks to align their axes with the flow. In some simulations and observations, narrow rivers of relatively cool gas thread hot halos to sustain high star formation rates in young massive systems, a process that reduces the need for mergers to explain rapid early growth. The James Webb Space Telescope has deepened the intrigue by finding very bright candidates at surprisingly early times. If many survive further scrutiny, they may imply unusually efficient conversion of gas into stars' quick assembly by smooth streams or unseen assistance from black holes that light up gas while adding mass. Voids once treated as leftover nothing emerge as quiet testbeds for cosmic physics. Their shapes, sizes, and tendency to cluster respond sensitively to the law of gravity and to the pressure of dark energy. Because void interiors evolve slowly, they preserve the memory of the initial conditions more cleanly than crowded regions do, allowing careful comparison to the predictions of the early ripples. Meanwhile, edges of voids act like dams where matter piles into thin walls, and the motion of galaxies away from these basins reveals how swiftly the web grows. As surveys expand, the mosaic gains depth. The European Space Agency mission Euclid and the Legacy, survey of space and time at the Vera C. Rubin Observatory, will map billions of galaxies and measure cosmic shear across most of the sky, turning statistical hints into sharp tests. Cross-linking these maps with the glow of hot gas, with counts of clusters, and with the forest in quasar spectra, will tighten the weave of evidence and either confirm the cold dark matter framework in detail or outline its limits. Whatever the outcome, the logic of emergence remains vivid. From an almost featureless beginning, gravity amplifies tiny numerical differences into grand contrasts. Feedback from stars and black holes moderates that growth to produce the diversity seen in the night, and the resulting web both remembers its origin and writes the conditions for what will follow. It channels material and heat toward places where chemistry can become complex, and it regulates those flows through bursts and pauses that echo across scales. The story retains an open edge. If dark matter is one particle, the pattern on very small scales will settle to a specific form. If it is a family, or if it interacts with itself or with light in a hidden way, the arrangement of dwarfs, the thickness of cores and the rhythm of growth will speak its name. If gravity changes behavior over very long distances, the measure of voids and the pace of structure formation will betray that change. If early star formation was more efficient than expected metals in the intergalactic medium, and the timing of the clearing of hydrogen will record that haste. Each possibility is bound to a distinct signature, and instruments now being built are designed to listen for those signatures in the quiet statistics of many millions of galaxies. Across all of this, the link to the beginning remains clear. The preferred separation set by ancient sound waves reappears in the spacing of structures today, a quiet rhyme that ties first light to the present lattice. Weak gravitational lensing adds an independent map because foreground mass subtly shears the images of background galaxies in a correlated way. Averaging many shapes reveals the same sheets and threads that galaxy positions imply. At cluster intersections, the story grows louder. Hot gas glows in high-energy light. Galaxies fall along filaments, and the combined gravity bends, passing beams into arcs that weigh the whole. Feedback from supernovae and central black holes returns energy to the gas and throttles star, making a counterforce, without which models would overproduce dense systems. Despite these successes, the web poses local puzzles. Some satellites gather in thin planes, some dwarfs show soft cores, and the most massive subhalos appear rarer than once expected. Together they hint at either selection effects and feedback working in concert, or modest departures from the simplest unseen matter. On very large scale, subtle tensions between the growth rate read from motions and shapes, and the inferred from the ancient sky, keep interest high in new surveys that will trace billions of sources. Across all of this, the link to the beginning remains clear. The preferred separation set by ancient sound waves reappears in the spacing of structures today, a quiet rhyme that ties first light to the present lattice. The invisible majority reveals itself by the way it pulls. In spiral galaxies, the luminous disks spin so fast that stars at large radii should drift away, if only the visible mass were present, yet they remain bound, and the rotation speed stays nearly constant with distance. This flat rotation curve implies an extended halo of unseen matter that adds gravity long after the starlight fades. The same inference arises in a different language when clusters of galaxies are weighed. The motions of member galaxies, the temperature of the hot gas that fills the space between them, and the bending of background light by the cluster's mass, each point to a reservoir far larger than the sum of stars and gas. When two clusters collide at high speed, the luminous gas lags behind because it collides and shocks, while the bulk of the mass marches ahead with the galaxies and reveals itself through gravitational lensing. This split, made famous in a bullet-shaped system and seen in others, acts like a laboratory experiment on the sky, showing that most of the mass is not ordinary and does not slow itself with collisions. On yet larger scales, the ancient afterglow of the universe carries a pattern of acoustic peaks, whose heights and positions announce how much matter existed and how it responded to gravity and pressure before atoms formed. The data fit a cosmos where an unseen component outmasses the familiar by about a factor of 5. In the growth of structure numerical experiments that include a cold and nearly collisionless component, generate the cosmic web with the right contrast across a wide span of scales, while models with only ordinary matter stall because radiation pressure in the early plasma prevents timely clumping. The story is therefore stitched from many lines of evidence that agree without sharing the same systematics, a convergence that makes the invisible matter feel as real as any star, even though its nature remains hidden. The smallest and faintest galaxies sharpen the case. Dwarf spheroidals around the Milky Way and its neighbours have so little light that their stars behave like test particles in a deep potential well. Their internal motions require a mass hundreds of times larger than what their stars would suggest. Strong lensing by galaxies and clusters throws this truth into dramatic relief by creating multiple images and arcs whose shapes demand mass profiles that extend beyond the visible. Weak lensing gathers the whisper of many slight distortions to map the same halo statistically. Meanwhile, the thinness and speed of rotating disks argue against a universe filled with numerous massive but dark compact bodies which would thicken and heat disks beyond what is seen. All signs point instead to a new form of matter that interacts with light only through gravity, and perhaps through forces too subtle to show themselves yet. Candidates fall into families that reflect different ways the unseen might keep to itself. One family imagines heavy particles born in the early fireball that froze out with the right abundance, a process that ironically relies on the ability of such particles to annihilate with their own kind, and disappear when the universe was much hotter and denser. These hypothetical relics, often called weakly interacting massive particles, inspire searches in deep underground detectors that wait for an occasional collision with a nucleus in telescopes that watch for excess pairs of high-energy photons or other debris from annihilations today, and in colliders that look for signs of missing energy when known particles recoil against an invisible partner. Another family turns to very light quanta that behave collectively as a field, as in the case of axions originally proposed to mend a symmetry puzzle in the strong nuclear force. These would act more like a wave than like a swarm of particles, and could alter small-scale structure by gently smearing density. Experiments place resonant cavities in strong magnetic fields to coax such quanta into detectable photons. A third line imagines a sterile version of the neutrino interacting even more feebly than the known species, and decaying so slowly that it remains present today, while leaving subtle fingerprints in the formation of small galaxies and in faint background light. There is also the possibility that the unseen lives in a hidden sector with its own forces, including a modest self-interaction that would let invisible particles scatter from one another within halos and soften their centers, perhaps addressing the tension between the steep inner profiles predicted by simple simulations and the flatter cores inferred in some dwarfs. The pull of evidence for a new component has provoked alternative ideas that alter gravity rather than adding matter. Modified dynamics and modified geometry can fit selected phenomena, particularly the way stellar mass tracks rotation speed in individual galaxies, but they struggle to account simultaneously for the lensing in colliding clusters, for the full pattern of peaks in the ancient afterglow, and for the detailed growth of the web across scales. The cumulative weight still favours a new matter species, even if the final answer may include a refined law of gravity at very long distances. The pursuit of the invisible has matured into a patient global effort that takes advantage of many messengers. Underground detectors buried beneath mountains and ice reduce spurious events from cosmic rays to a trickle, and have reached sensitivities that would have seemed implausible a generation ago. Each time a swath of parameter space is excluded, theorists adjust expectations, and observers shift tactics, adding directional sensitivity or new target materials in search of rare nuclear recoils or tiny ionization signals. Indirect searches face the challenge of astrophysical backgrounds that can mimic or mask a faint annihilation glow, yet they continue to monitor the centers of galaxies, dwarf spheroidals and clusters across multiple wavelengths. Collider searches probe for missing energy events and exotic cascades, though the absence of a clear signal so far has pressed the simplest versions of the heavy relic picture. Gravitational lensing and stellar dynamics meanwhile improve the mapping of halos, revealing substructure that acts as a fingerprint of the unseen. Cold dark matter predicts numerous small clumps, some too light to shine. Their presence can be inferred when they perturb lens darks and cause characteristic kinks. The tally of such subhalos tests both the particle's warmth and its interaction strength. The cosmic web itself has become a crucible. If the unseen is warm rather than cold, its early motion washes out structure on small scales, reducing the number of faint galaxies and altering the texture of the intergalactic medium. Surveys of the forest of hydrogen absorption toward distant quasars set limits on such free streaming. If the unseen scatters with itself, halo centers become rounder and less dense. Strong lensing and the internal kinematics of dwarfs probe this by comparing core sizes across environments. If the unseen interacts weakly with radiation, the precise shape of the peaks in the ancient afterglow changes. Satellite maps have already trimmed such possibilities. Across these tests, the emerging picture remains that the invisible behaves like a cold, slow component that clusters early and deeply, yet the door to subtle complexity stays open. The philosophical temptation to claim that nothing more than gravity is needed still founders on the data, but the empirical spirit remains careful because nature has surprised before. Here the intrigue grows in two directions at once. On the one hand, the invisible component appears essential to the existence of galaxies' clusters and the web itself. Without it, the timing of structure would not work. On the other hand, the very success of the framework raises tensions that point to the fine print of the unseen, the density of the smallest cores, the arrangement of satellites in occasional planes, the slightly slow growth rate hinted by lensing statistics in some surveys compared with expectations from the ancient sky. These are not fatal, but they are persistent, and they turn the silent hand into a teacher with a soft voice. The resolution may be patient details in baryonic feedback that rearrange mass more than expected, or a modest self-interaction in the dark sector, or a hint that the simplest initial conditions lacked a small feature. The outcome will be empirical. Instruments will count more dwarfs, map more lenses, measure more shapes, and listen more carefully for the faint tap of a collision in dark halls beneath the mountains. In all of this, the central fact holds steady the stars. Gas and dust that catch the eye are ornaments on a deeper structure, and that structure reveals itself not by shining, but by shaping the possible. The universe grows into what the invisible allows, and the question of what the invisible is sustains one of the clearest bridges from the first tremors of nothing to the richness that follows. The slow push that speeds the universe emerges from candles that do not flicker. In the late 20th century, teams measure the brightness of distant explosions called Type 1, a supernovae stellar detonations that reach nearly the same peak luminosity because the physics of their ignition is regulated. By comparing the apparent brightness of these standard candles to their redshift, observers reconstruct how the expansion has changed over time. The result surprises everyone. Distant supernova look dimmer than a steadily decelerating universe would allow, as if they are farther away than expected. The simplest reading is that the expansion has begun to accelerate in the recent cosmic past. The ancient afterglow of the universe mapped across the whole sky independently prefers a flat large-scale geometry, and the spacing of galaxies carries a fossil ruler from primordial sound waves that fixes distances across time. Together, these anchors require an extra ingredient that behaves not like matter, which clumps, but like a smooth pressure that does not dilute as rapidly, and exerts a kind of anti-gravity on the larger scales. This ingredient earns a plain name, dark energy, because it hides in the vacuum and is inferred by its effect rather than by its light. In the language of gravity, what matters is not only energy density but also pressure. Ordinary matter and radiation pull because their pressure is either small or positive, but a component whose pressure is negative and large in magnitude can drive acceleration by pushing on the fabric of space. The simplest such component is a constant energy of the vacuum itself, the cosmological constant long ago introduced and later abandoned, now reinterpreted as a natural candidate. A pure constant has an equation of state whose pressure is exactly the negative of its energy density. In words, it remains the same everywhere and everywhen, and it never clumps. More nuanced possibilities imagine a field that slowly rolls, changing its energy and pressure gently over time, or a modification of gravity that imitates a smooth push without introducing a new substance. Each option must face the same suite of tests, the distances to supernova, the angular sizes and acoustic peaks in the ancient afterglow, the yardstick of the fossil ring in galaxy, clustering the way the growth of structure proceeds as measured by weak gravitational lensing and by the motions of galaxies, and the pattern of how gravitational wells imprint themselves on the afterglow through late-time effects. When these tests are combined, they paint a consistent picture of a universe where ordinary matter is only a small share. Unseen matter is roughly 5 times larger than the ordinary share, and dark energy fills most of the budget and acts like a nearly constant background. Yet the word nearly keeps curiosity alive. Measurements of the local expansion rate built from distances that step outward from nearby pulsating stars to supernovae and then to far galaxies tend to yield a value somewhat higher than the rate inferred by interpreting the ancient afterglow in the standard model. This difference has persisted as data have improved, suggesting either an unrecognized systematic error or new physics that changes the expansion history between the time of the afterglow and the present era. Speculative remedies include a brief episode of additional energy density before atoms formed, sometimes called early dark energy, that would slightly alter the scale of the acoustic features, and thus the inferred rate today, or gentle interactions among components that shift energy subtly over time. Meanwhile, measurements of how fast structure grows, inferred from cosmic shear in the shapes of faint galaxies, and from the tendency of galaxies to fall together, sometimes hint at a growth that is a little slower than the simplest reading of the ancient afterglow would suggest. The hints are not decisive, and different surveys do not always agree, but the pattern has stirred interest in whether gravity weakens slightly on large scales, or whether dark energy evolves in a way that slows clustering. The observational campaign is deliberate and broad because subtle biases can masquerade as discovery. Supernovae must be standardized with care by correlating light curve shapes and colors, with peak brightness and dust in host galaxies must be accounted for. The fossil ring in galaxy clustering requires precise distance measurements and huge samples to beat down noise. Weak lensing demands exquisite control of the shapes of millions of galaxies, correcting for the blurring and stretching introduced by telescopes and atmosphere. The ancient afterglow brings its own foregrounds, including dust and synchrotron emission, in our own galaxy that must be modelled and removed. Across these challenges, independent teams using different instruments converge on the same broad truth. There is a smooth component that dominates today and pushes the expansion faster. It behaves very much like a cosmological constant, with an equation of state close to the exact negative ratio, and any change with time must be slow if it exists at all. If the push is the energy of the vacuum itself, a new and old puzzle returns with force. Why is the value so small compared with naive quantum estimates, and why is it not exactly zero? The coincidence that the density of the vacuum is of the same order as the current density of matter, even though one dilutes as the universe expands and the other does not, also raises an eyebrow. Some see anthropic selection in a landscape of possibilities where only in rare pockets is the vacuum energy small enough to allow galaxies and stars to form before expansion, tears potential structures apart. Others seek a symmetry or a dynamic adjustment that sets the value near zero and then leaves a small residue. No proposal has yet convinced the community with both elegance and testable predictions, and so the simplest model remains the working guide while the search for cracks continues. If the push instead arises from a slow field sometimes called quintessence, it would roll down a potential and change its pressure over time. The equation of state would deviate slightly from the constant value and perhaps evolve. Surveys can constrain such deviations by checking whether distances and growth as functions of time follow the single constant pattern or bend. So far, the allowed room for bending is narrow. Modifications to gravity on large scales would change the relation between the way geometry behaves and the way matter clumps. Tests that compare the lensing potential to the motions of galaxies, or that track how deep gravitational wells imprint additional temperature patterns on the ancient afterglow as they evolve, probe this possibility. Current data allow only small departures from the standard law over the ranges explored, yet they do not close the door entirely. The next decade of observation is designed to press these questions. The European Space Agency mission Euclid is mapping billions of galaxies with sharp imaging and spectroscopy to measure cosmic shear and the fossil ring across a great volume of space. The Vera C. Rubin Observatory will add time to depth by repeatedly scanning the sky for years, allowing exquisite studies of lensing and clustering and discovery of new supernovae by the hundreds of thousands. The Nancy Grace Roman Space Telescope will combine space-based stability with wide fields to refine weak lensing and supernova distances with independent systematics. Together with ever more detailed analyses of the ancient afterglow, and with catalogues from the Dark Energy Survey and other efforts, these missions will test whether the equation of state departs from the constant value by even a few percent, and whether the growth of structure carries telltale fingerprints of new physics. There is an aesthetic humility in this chapter of the story. The force that shapes the largest pattern in the late universe leaves no local trace that can be bottled in a laboratory or imaged in a telescope except through its influence on everything else. It does not clump, it does not shine, it does not scatter it, only sets the stage on which light and matter weave. Its most likely identity is the energy of the vacuum, that subtle background already implicated in the early sprint and in the odd arithmetic of quantum fields, but its measured value mocks our calculations and its origin remains obscure. If the answer is a rolling field, the law for its potential seems handwritten for calm, and if the answer is a change in gravity, the change must be furtive. Yet the slow push is also a kind of gift, because it turns the cosmos into a laboratory where patience can be traded for precision. Each supernova captured each galaxy shape, measured each acoustic ridge, counted, tightens the net. Either the push will continue to look exactly like a constant, and the embarrassment of its small value will stand as a clue to a deeper principle, or a small deviation will emerge and point toward a story where the vacuum is not entirely still. In either case, the mystery deepens the link between nothing and everything, because the very emptiness of space carries agency. The universe does not only expand into nothing, nothing expands, and in doing so it guides the fate of all structures that rise from the first ripples to the present web. First light dawns not as a single sunrise, but as a slow ignition scattered across the young cosmos, where the first stars kindle in dark halos and begin to change the chemistry of everything that follows. The universe, once a cooling fog of hydrogen and helium with almost no heavier elements, reaches a threshold where gas falling into the knots of the growing web compresses, radiates its heat, and finally tips into collapse. In those earlier star-forming clouds there is no dust to shield, no metals to cool efficiently, and so the first stars are expected to be massive, short-lived and bright, a generation that astronomers call primordial. Their light leaks into the surrounding hydrogen, carving out bubbles of ionized gas and thinning the fog that once blocked long journeys for photons. Over time, these bubbles expand and merge, and the era of reionization progresses from a patchwork of clearings to a near-transparent universe. The pattern, speed, and patchiness of this clearing hold the memory of how quickly galaxies assemble, how fiercely they form stars, and how readily their ultraviolet photons escape into the intergalactic medium. Clues gather from many directions. The spectra of very distant quasars show deep troughs where neutral hydrogen absorbs, and the depth of those troughs changes with time in a way that charts the end of the fog. The ancient afterglow of the universe carries a faint scattering signature that estimates the total column of free electrons produced by early ionization. In the radio experiments, hunt for a global dip in the background light from neutral hydrogen as the first stars heat and ionize their surroundings. Arrays on quiet plains and deserts try to map the three-dimensional structure of this faint glow and its disappearance. Meanwhile, deep surveys in the near-infrared reveal small galaxies at surprisingly early times, some brighter than anticipated with colors and sizes that challenge models that expected slower assembly. The James Webb Space Telescope, launched to see precisely this era, peels back the darkness with mirrors and detectors cooled to unveil wavelengths stretched by cosmic expansion. It finds compact sources whose light suggests heavy ongoing star formation when the universe is only a tiny fraction of its present age. Some candidates appear too luminous and too abundant for comfortable models, implying either bursts of extraordinary efficiency, assistance from black holes feeding at their centers, or a need to refine how distances and stellar populations are inferred in this new regime. Spectroscopy adds weight by identifying emission from hydrogen lines and from oxygen and neon, which not only confirm distances, but also reveal the chemical poverty of these systems. The presence of any oxygen or carbon at all means that at least one prior generation of stars must have lived and died already spreading ashes into their environment. With the Atacama Large Millimeter Array observers detect faint dust and molecular gas in some early galaxies, a sign that the cycle from massive star to supernova to enriched cloud has already begun. At the same time, vast stretches remain metal, poor preserving the conditions for pockets of truly primordial star formation to continue in the shadows of brighter neighbours. The first heavy elements matter because they change the cooling channels of gas. A trace of carbon or oxygen can allow a cloud to radiate heat and fragment into many smaller clumps, leading to a distribution of stellar masses more like what is observed in later epochs. Without those metals, a cloud collapses less efficiently and favours more massive stars. The transition from a top-heavy initial mass function to a more familiar one is therefore both a chemical and a dynamical turning point, and it leaves marks in the light of galaxies, in the statistics of supernova, and in the eventual presence of long-lived low-mass stars that can still shine today as fossils. Astronomers search the halo of the Milky Way for ancient stars with extremely low metal content, trying to read their surfaces like tree rings for hints of the first enrichment events. Some of these survivors carry unusual ratios of elements that point to exotic explosions or to mixing in the earlier supernova. Their existence argues that the first star-forming clouds did not always form only giants. Some small stars must have emerged where metal lines molecules or dust allowed more efficient cooling even in a nearly pristine medium. Black holes arrive early as well. Quasars powered by black holes of 1 billion solar masses blaze when the universe is still young, demanding rapid growth. Either light seeds from massive primordial stars feed at rates near the maximum allowed, and concentrate matter efficiently, or heavier seeds form through direct collapse of gas in special conditions, where fragmentation is suppressed and angular momentum is removed. The ultraviolet radiation from these accreting giants adds to the ionizing budget and sculpts their neighborhoods, while winds and jets carry energy back into their host galaxies and out into the surrounding medium. Quiet black holes in less extreme systems may also help by stoking turbulence and driving outflows that regulate star formation, while leaving the global luminosity higher than starlight alone would predict. The rhythm of first light thus ties together the assembly of dark matter halos, the thermodynamics of gas, the chemistry of enrichment, and the feedback from both supernovae and accreting black holes. Each element speaks through a different messenger. Hydrogen lines trace ionization fronts and reveal how easily photons escape. Oxygen and neon lines disclose metallicity and the hardness of the radiation field. Millimeter detections of dust and carbon monoxide indicate reservoirs for future stars. Morphologies suggest mergers or smooth flows. Weak lensing of background sources by these early systems hints at the mass of their halos. The challenge is that selection effects inevitably favor the more luminous and compact, while the bulk of the ionizing work may be done by modest galaxies below current detection limits. Models that match the measured timeline often require a steep rise in the number of faint galaxies, each contributing a trickle of photons that becomes a river in some, provided that their star-forming regions are porous enough for light to escape. The escape fraction, a plain phrase that hides detailed physics of geometry and dust, becomes a central number. Observations of local analogues and of slightly later dwarf galaxies offer hints, but the true value at the dawn of galaxy formation remains under debate. Another thread connects to the intergalactic medium temperature. As bubbles expand and overlap, the gas between galaxies warms. Later, as the universe stretches, that gas cools. Sensitive measurements of the small-scale structure in the absorption seen toward distant quasars trace this thermal history and therefore constrain the pace and character of ionization. If hard photons from black holes contribute significantly, the heating is different than if stellar ultraviolet dominates. If metal-poor stars produce more high-energy photons, their role grows. Each scenario leaves a slightly different fingerprint in the temperature and ionization state over time. Even as the region near the beginning grows crowded with discoveries, anomalies protect the mystery. Some claimed galaxies appear massive and mature too soon, as if either star formation raced ahead or black holes and bursts of dust-heated gas masquerade as older stellar populations. Photometric redshifts can mislead when only a few filters are available, and spectroscopic confirmation sometimes revises distances downward, but a residual tension remains that encourages a fresh look at star formation efficiency, feedback strength, and the influence of environment within the early web. The satisfaction of this era is that instruments now cross-check one another. Space-based infrared images pinpoint candidates. Ground-based spectrographs collect lines that fix their place in time and measure their chemistry. Millimeter arrays weigh their cool gas and dust. Radio experiments sketch the glow of hydrogen as it changes state. Piece by piece, first light shifts from a mythic phrase to a measured process with irreducible wonder left intact. At its heart lies a simple exchange. Gravity gathers fuel, radiation and explosions push back. Metals open new channels. Black holes stir the pot, and the fog lifts. The universe steps from opacity to transparency because countless small engines switch on and keep running long enough to change the medium they inhabit. The first stars do not just shine, they write. They imprint metals into space, they thicken clouds into diverse fragments, they establish the terms under which galaxies continue to grow. The journey from almost nothing to the intricate present passes through this furnace of brief giants and stubborn dwarfs, and every later planet owes its rocks and oceans to those first short-lived suns that died before there were eyes to see them. In the young universe, black holes appear as if arriving before the factories that usually build them engines, roaring before assembly lines exist, and their presence forces a reckoning with speed. Observers see quasars blazing when the cosmos is only a small fraction of its present age, powered by black holes with masses of 1 billion suns or more. To grow so heavy so soon, a seed must either start large or feed without long pauses at a rate close to the physical ceiling set by the balance between gravity and radiation pressure. The most straightforward path begins with the death of very massive primordial stars whose cores collapse into black holes a few hundred times the mass of the Sun. If these light seeds live in halos that deliver gas steadily, and if they are not kicked from their cradles by asymmetrical explosions or mergers, they can in principle grow by accreting gas and swallowing smaller companions. The clocks, however, are stern. Feeding near the balance point with typical efficiencies, a black hole doubles its mass on a timescale of tens of millions of years. To reach 1 billion suns within a few 100 million years requires sustained access to fuel without the interruptions that feedback and dynamics often impose. The alternative imagines heavy seeds formed when a gas cloud kept hot and dense in a special environment where cooling and fragmentation are suppressed, collapses directly to a black hole of 100,000 to 1 million solar masses. Such environments could arise in halos bathed in intense ultraviolet light that prevents hydrogen from forming molecules which are needed for cooling to modest temperatures. Without molecules, the gas remains warm, pressure supports it against small-scale fragmentation, and inflow can proceed almost monolithically to a central object. In either case, the feed must continue. Accretion flows carry gas inward, while radiative heat winds and jets carry energy outward, a dance between gravity and feedback orchestrated by the geometry of the flow and the spin of the black hole. Thick and turbulent disks can hide the central engine from some lines of sight, and allow inflow to exceed the notional ceiling for short times if radiation leaks preferentially through funnels, while matter continues to rain inward through dense optically thick streams. In such phases, growth can be rapid. Mergers between black holes add mass, but they also can kick the remnant through gravitational recoil, and a strong kick may eject it from a shallow potential while slowing future growth. The overall outcome depends on the merger history, the depth of the host halo, the spin alignment of the participants, and the geometry of accretion. Observations provide both constraints and provocations. Spectra of distant quasars reveal broad emission lines from gas moving at thousands of kilometers per second, and the brightness and line widths imply the presence of very massive black holes. Some of these systems also exhibit metal lines indicating that their surroundings are already enriched, meaning at least one generation of star formation has taken place, recycled its ashes, and perhaps fed the engine. Their host galaxies are difficult to image in detail at such distances, but in some cases there are hints of compact, intensely star-forming environments, as if the black hole and its galaxy grow together in a rapid interlaced episode. At slightly later times, high-resolution millimeter views show cold gas reservoirs swirling in rotating structures that feed central regions, and the coupling between black hole outflows and star-forming gas appears to regulate the pace of both. The idea that the brightness of a galaxy's central bulge correlates with the mass of its black hole seen clearly in the present universe suggests long-standing coevolution. Whatever mechanisms turn gas into stars also funnel a fraction inward, and in turn energy from the central engine pushes outward to shape the next round of star formation. The impact of black holes spreads beyond their neighborhoods. Jets drill channels through interstellar gas, and sometimes pierce the halo-inflating bubbles that shine in high-energy light, and stirring turbulence that heats gas and prevents it from cooling too quickly. At cluster scales, these outflows carve cavities in the hot intra-cluster medium and keep massive reservoirs from collapsing into stars too rapidly, solving the old cooling flow problem by replacing a naive cascade with a feedback loop. At earlier epochs, the same physics acts in miniature, where winds and jets from feeding black holes may clear paths that allow starlight to escape more easily into the intergalactic medium, thereby helping to lift the fog of neutral hydrogen that pervaded space after atoms first formed. If so, the contribution of black holes to reionization is not dominant but not negligible, a modulation of the stellar chorus that changes the shape of the clearing. On the scale of the cosmic web, black holes at intersections can accelerate the heating of gas that arrives along filaments, making future inflow less steady and more episodic, which affects how galaxies assemble their disks and bulges. The early appearance of heavy black holes also raises questions of demographics. If only rare conditions allow heavy seeds, why do luminous quasars appear in large numbers when the universe is very young? If instead many light seeds form, how do enough of them avoid ejection and starvation to reach the highest masses so quickly? Gravitational wave observatories will add a new way to count. Mergers of intermediate mass black holes in the young universe should produce ripples in space-time at frequencies that planned space-based detectors can hear, and their rate and mass distribution will help distinguish between a history dominated by heavy seeds with fewer mergers and a history populated with many light seeds that combine often. Meanwhile, precise timing of radio pulses in networks may catch the deep hum of giant black hole pairs as they enspiral in galactic centers at later times, providing an integral measure of the assembly of massive engines. Another layer of intrigue involves the spin of black holes. Spin carries memory of the last episodes of growth. Gas inflow, in a steady direction, tends to spin up the hole, while chaotic episodes with changing directions can spin it down. Spin in turn shapes the efficiency of accretion and the power and collimation of jets. X-ray spectra of accreting black holes can reveal spin through the shape of broadened iron lines, and the distribution of measured spins across cosmic time may tell whether early growth was orderly and aligned or patchy and stochastic. If the very earliest seeds arise from direct collapse, they may begin with low spin due to isotropic turbulence, or high spin if angular momentum is not fully shed. Either case has implications for how they illuminate their surroundings. Even as the big picture takes form, anomalies provoke care. Some claimed hosts of bright early black holes seem lower in stellar mass than the mass of their central engines would predict by the present-day relation, hinting that black holes may sometimes lead and galaxies follow, especially at early times when gas inflow is strong and regulation has not settled. Conversely, there are massive galaxies with underweight black holes suggesting that growth can lag as well, perhaps when gas arrives in a way that favors star formation over funneling to the center. The scatter in these relations may grow with redshift, a natural outcome of a coevolution that proceeds by fits and starts, rather than by a smooth curve. The synthesis that emerges is not a single path but a weighted set of channels. In some corners, light seeds feed hard, perhaps aided by brief, supercritical bursts that slip under the limit by geometry, and they reach great size by endurance. In others, heavy seeds form under the stern light of a neighboring starburst that suppresses molecules and lets a single cloud collapse, leapfrogging the earliest hurdles. Mergers stitch these histories together while feedback sculpts the timing. The black hole is not an afterthought carved from the stellar city. It is a resident whose appetite and anger help determine the skyline. That the earliest engines appear so soon does not break the chain from nothing, it tightens it, because it shows that once gravity has a scaffold and gas has a path, complexity accelerates. A dark core that by itself cannot emit light becomes a lamp by arranging for matter to fall. In doing so, it announces that the route from near uniformity to blazing structure includes shortcuts that nature takes whenever conditions allow. The darkness at the center becomes a method, and the method leaves signatures across the spectrum and across time that instruments continue to collect, interpret, and argue over, bringing the impossible noon of early quasars into the same story, where atoms first formed and light first went free. The local story begins as a small thread woven from the larger web, a cold and dusty knot inside a giant molecular cloud that drifts in a spiral arm of the galaxy. Gravity gathers this knot until it cannot hold its own weight, and the cloud core sinks inward, while a trace of spin flattens the infall into a broad disk around a growing star. In the center, a protostar brightens behind a veil of gas. In the disk, dust grains collide and stick, first gently, then with more commitment, as electrostatic forces and frost coatings help pebbles become stones. Stones become boulders, and boulders amalgamate into planetesimals that pull by gravity as much as they push by chance. The young sun enters a stormy phase when magnetic fields tangle and unwind, flinging wind and light that scour the innermost disk. Close to the star, heat drives away water and carbon-bearing ices, leaving rock and metal to dominate. Farther out beyond the line where water vapor freezes, ice loads the solids, and growth accelerates. The disk is not a quiet conveyor belt, but a living environment where spirals, shocks, and pressure traps herd material into rings and eddies, concentrating pebbles so that gravity can finish the job. In this early factory, clocks invisible to the eye keep time by the decay of short-lived isotopes. Aluminum-26 transmutes into magnesium-26 in a handful of million years, and the ratio of parent to daughter, recorded in ancient inclusions inside meteorites, serves as a stopwatch for the first events. The very oldest solids yet found bright calcium and aluminum-rich specks, preserved in primitive stones called carbonaceous chondrites, date the dawn of the disk to roughly 4.5 billion years in the past, with precision fine enough to distinguish steps within the first few million years. These inclusions and the glassy spherules named chondrules carry oxygen isotope patterns that do not sit on the simple line expected from a single, well-mixed reservoir, a sign that the early disk was a patchwork of environments where ultraviolet light gas chemistry and dust evolution tug the balance among the three oxygen isotopes in different directions. The magnetic memory locked inside some chondrules tells of strong fields threading the disk, likely dragged and wound by the infus and by the early wind of the sun, and that memory implies that turbulent transport and magnetically driven jets helped move material inward and outward, mixing zones that would otherwise remain separate. This mixing matters because the ingredients of the planets are assembled from far-ranging sources. Samples of comet dust returned by a mission under the National Aeronautics and Space Administration show high-temperature minerals, forged close to the sun, embedded in a matrix of ices and organics, formed in deep, cold, clear evidence that dust was carried outward into the freezer and then trapped. Spacecraft from the Japan Aerospace Exploration Agency and the National Aeronautics and Space Administration have snatched grains from near-Earth asteroids and sealed whole cupfuls of regolith, to return revealing a spectrum of rocks from pristine to thermally altered, rich in organic compounds and in prebiotic molecules. The European Space Agency guided a robot to a comet and watched as jets carried off gas and dust, while surface layers crumbled under sunlight, and it measured abundant organics and complex chemistry in the vapor. In the spectrum of the heavy water to light water ratio comets and asteroids scatter some matching Earth-like ratios, others standing apart. No single type of object owns the recipe for the oceans, but a mixture of sources can paint the right balance. Inside the snowline, multiple pathways sculpt the final architecture. Embryonic planets the size of Mars collide, merge, and scatter in a dance choreographed by the gravity of the growing giants beyond. Models that allow Jupiter to wander inward and then retreat shepherded by the resonant pull of Saturn can explain why the asteroid belt holds little mass yet spans both dry and hydrated rocks, and why the inner planets are relatively small compared with the giants. Farther out, the giant planets may have traded places under the pull of the leftover disk and of their mutual resonances, rearranging the orbits of countless icy bodies and sprinkling debris into the inner regions in a protracted bombardment. Lunar craters record that history, though the notion of a singular spike called a late heavy bombardment has softened into a more extended and complex tale of impacts. The Earth's oldest minerals, tiny zircons preserved in ancient rocks, hint that crust and perhaps even liquid water appeared surprisingly early, within a few 100 million years of the first solids, suggesting that conditions suitable for complex chemistry stabilized quickly despite catastrophic collisions. One of those collisions, the leading explanation for the origin of the Moon, likely involved a Mars-sized embryo striking the young Earth and spraying vaporized rock into orbit where it coalesced. The isotopic near identity of lunar and terrestrial rocks remains a constraint that any origin scenario must honor. Through this long assembly, the Sun matures from a veiled protostar into a stable main sequence furnace. Its radiation and wind carve away the remaining gas in the inner system and blow a bubble into the surrounding medium. The protoplanetary disk thins and disappears over a span of only a few million years, a disappearance observed in young stellar clusters where stars of different ages exhibit disks with varying masses and lifetimes. What remains are planets, moons, asteroids, comets, and the dust of collisions, all imprinted with the early thermal gradient and with the memory of migrations and resonances. The inner system is rocky and metal-rich. The outer system wears mantles of ice and swaddles cores in deep atmospheres of hydrogen and helium. This tidy summary masks lingering riddles that keep the local story connected to the wider mystery. Mercury carries an outsized iron core that implies either formation in a metal-rich pocket or stripping of silicate mantle through giant impacts or searing by the early sun. Mars is small compared with models that do not include giant planet migration, a clue that the inner disk may have been truncated or the material redistributed by early wandering giants. The asteroid belt is a museum of contrasting origins, with dry and wet objects, primitive and altered stones resting side by side, because the belt is not a birthplace, but a sieve that held what other processes could not finish. Jupiter's core had to form quickly enough to accrete a thick atmosphere before the gas vanished, yet not so quickly or so heavily as to gulp the whole neighborhood. Measurements of noble gases and heavy elements in its air by arriving probes guide models of formation and of inward and outward motion. Rings and moons around the giants tell of ongoing assembly, with young surfaces like that of Enceladus, and the ocean within Europa, hinting that energy from tides and radioactivity keeps chemistry lively long after formation. The most intimate traces of the early sun come on the wind. Solar wind ions implanted in lunar soil and in the topmost layers of airless rock serve as stamps of the evolving output of the star. Paleomagnetic records on Earth indicate that our planet's field shielded the surface from the brunt of this wind, preserving an atmosphere and helping water persist. The balance between a thick atmosphere plate motions that recycle carbon dioxide between rocks and air, and a steady star sets a long habitability that seems contingent yet robust, a balance that has been reset by impacts and volcanism, yet restored by the cycling of water and carbon. The narrative does not treat Earth as destiny, but as one drawn from a distribution set by the physics of disks and the collective life of a planetary system. The lamps that patrol the outer dark comets stored in distant reservoirs occasionally fall inward to deliver fresh organics and water, while also posing hazards. The Murchison meteorite and others like it carry amino acid sugars and a menagerie of carbon molecules cooked in small bodies where heat from aluminum-26 and shocks from collisions set reactions running in liquid veins. These organics do not prove life, but they prove that the chemical alphabet is widespread and eager, and that planetary surfaces inherit more than stone from their birth environment. When the question returns to how something rose from almost nothing here, the answer is a chain rather than a leap. A filament of the cosmic web funneled gas into a cold knot. Gravity collapsed a core and spun a disk. Turbulence, magnetism, and radiation sculpted that disk, while isotopic clocks ticked. Pebbles gathered, planets accreted, giants migrated, and leftovers bombarded. Winds cleared the stage, and what remained evolved under the light of a settling star. The dates and ratios etched in meteorites, the shapes of craters, the chemistry of comets, the magnetism frozen into early solids, and the alignments of planetary orbits together turn the solar system into a narrative written in many inks. It is a story that looks inward to explain a home, and outward to connect that home to the great pattern, where the same rules that forged the first metals in early stars dictated the minerals in ancient rocks and the water in modern seas. Water, carbon, and heat join as a quiet conspiracy that steers simple matter toward complexity, and the laboratory is not a bench on Earth, but the wide stage of disks, comets, asteroids, and ocean worlds, where energy arrives in pulses rather than in flames. In a young protoplanetary disk, starlight shocks and grains cooperate to turn a thin mix of hydrogen, carbon, monoxide, water vapor, and nitrogen into a pantry of richer molecules. On the faces of dust grains, atoms stick, migrate, and meet. A layer of frost becomes both glue and catalyst. Ultraviolet light from the infant star cracks simple species, and the fragments recombine in patterns set by temperature and density gradients, so that inner regions cook quickly, while outer regions write slowly in ice. Observatories under the European Southern Observatory and arrays of dishes on high deserts have mapped rings of carbon, monoxide, carbon dioxide, water, and organic molecules around young stars. Some rings track where frost lines sit and drift. Others track where pressure traps corral pebbles, so that chemistry rides inside clumps that also grow bodies. Missions report that even in cold clouds, before a star forms complex organics already exist, including simple alcohols and esters, so the disk begins enriched rather than bare. As pebbles become planetesimals, heat from short-lived isotopes wakes chemistry inside. Aluminum-26 decays and warms small worlds until buried ice melts, and liquid water circulates through rock. Through a process called serpentinization, water meets olivine and pyroxene and produces hydrogen gas and alkaline fluids rich in dissolved metals. The reaction opens pores and generates gradients in temperature and in redox state that are engines for further reactions. Carbon monoxide and carbon dioxide in the presence of iron and nickel on grain surfaces or within freshly fractured rock can undergo reactions that build longer carbon chains a geologic cousin of processes used in industrial synthesis. On the surfaces of small bodies, ultraviolet light and charged particles from the young sun strike ices of water, methane and nitrogen, bearing compounds, rearranging them into a tarry residue that contains rings and chains known as polycyclic aromatic hydrocarbons and more elaborate precursors. When meteorites carrying that residue fall to Earth, they bring amino acids, sugar-related molecules and nitrogen-rich aromatics, each carrying isotopic fingerprints that point to low-temperature chemistry in space, rather than to contamination. Some of these compounds exhibit an excess of one-handedness over the other, a small chiral preference that may reflect circularly polarized light in star-forming regions, or asymmetric reactions on specific mineral faces. The delivery is not a one-time gift, but a drizzle that goes on for hundreds of millions of years, with each impact a test tube shattered across stone. Comets add their own inventory. Measurements of water, carbon dioxide, carbon monoxide, ammonia and organics, venting from comet nuclei, show that these bodies are layered archives of the outer disk. Dust returned from a short-period comet contained high-temperature grains, born near the young sun, proof that material migrated outward early and froze into distant reservoirs. The ratio of heavy water to light water varies among comets and among hydrated meteorites. The Earth's oceans can be reproduced by mixtures from several sources, suggesting a blended origin rather than a single courier. In the outer system, moons wrapped in ice carry heat produced not by sunlight but by tides. Resonances among orbits pump flexing energy into rocky cores and icy mantles. On Europa, fractures crisscross a surface young enough to suggest ongoing resurfacing. Salty deposits and coloured streaks hint at exchanges between an ocean below and the skin above. On Enceladus, geyser-like plumes vent water vapour and ice grains from fractures near the South Pole. A spacecraft under the National Aeronautics and Space Administration flew through those plumes and found salts, silica nanograins that point to hot water interacting with rock and organic molecules, ranging from small chains to more complex fragments. The combination of liquid water, rock and heat inside a small moon sketches the same ingredients that terrestrial hydrothermal systems exhibit, only written in cryogenic ink. Titan shows another branch of strangeness, with lakes of hydrocarbons under a methane sky, and complex photochemistry building hazes that settle like snow. Though Titan's surface is too cold for liquid water, models suggest transient melt layers during impacts, and buried aquifers where ammonia and water mix to lower the freezing point, creating pockets where organics and liquid meet. Farther out, Pluto and similar bodies show signs of past or present internal oceans beneath nitrogen and methane frost, and bright patches that may record frost migration and slow climate cycles. Heat does not have to be hot to be potent. It has to be organized and sustained, and tides deliver both. In the nearer past of Earth, alkaline vents along mid-ocean ridges and in serpentinized crust produce microporous minerals that act like natural electrochemical cells. Carbon dioxide reduced by hydrogen makes methane and longer chains. Gradients in pH and in potential across thin mineral walls can drive reactions that accumulate energy in bonds. While oceans and atmospheres change, these engines can tick for long spans. The same logic applies on ocean worlds where radiolysis can split water into reactive fragments that feed further steps. The young sun's radiation, though harsher than today, can also be a sculptor rather than a destroyer when filtered by a sky rich in volcanic gases. On a young Earth with intermittent shallow ponds and tides, cycles of wetting and drying can concentrate solutes and push condensation reactions that would falter in dilute solutions. Minerals such as clays and iron sulfides contemplate arrays of molecules so that order emerges from mess. No single setting owns the truth. The point is that many settings provide the same ingredients in different proportions, and history can be a tapestry woven from overlapping venues rather than a single cradle. Observations beyond the solar system strengthen the sense that this chemistry is not rare. Space telescopes have measured water vapor, methane, carbon dioxide, and other molecules in the skies of giant exoplanets, even when those skies are scalding by human standards. Each detection proves that elements assemble into familiar bonds wherever conditions allow. Around young stars, spectra reveal acetylene hydrogen cyanide and simple sugars in warm inner disks, while colder outer disks carry methanol, formaldehyde, and complex organics locked in ice. Some detections show gaps and rings where planets are likely forming aligning chemistry and dynamics in one view. The emerging map links carbon, water, and heat to the same structures that gravity draws. Water sets the phases of matter and the flow of solvents. Carbon offers a flexible alphabet for chains, rings, and frameworks. Heat from radionuclides, tides, and starlight supplies energy in controllable quanta. Together they generate far from equilibrium conditions where patterns can accumulate. None of this asserts that life follows automatically. Instead, it shows that the steps toward complexity are not exotic. They begin in space, on dust, in warm ice, in irradiated skins, and then continue inside rocks and oceans on worlds that keep energy flowing. When the question returns to how everything starts from almost nothing, this chapter supplies a sober answer. First, there must be a way to couple gradients to chemistry, and to shield the results from immediate erasure. The cosmos supplies both widely and early. The same fields and flows that drew galaxies and stars into being also created niches where molecules learn to persist. The surprise is not that complex carbon exists. The surprise would be if it did not, given how many engines work quietly in the dark. Earth's balance begins with motion beneath the feet. The planet sheds its internal heat through a slow conveyor of rock called plate tectonics, where the thin outer shell breaks into plates that move, collide, and dive. At mid-ocean, ridges' mantle melts and builds new crust. At subduction zones, old seafloor sinks back into the deep. This cycle drags surface carbon into the mantle as sediments and carbonates ride down, then returns it through volcanoes and weathering as mountains rise and grind. The carbon dioxide in the air dissolved in rain reacts with silicate rocks to form carbonates, a process that removes greenhouse gas when temperatures run warm, and slows when temperatures run cool, a planetary thermostat that stabilizes climate over millions of years. Without this exchange, carbon dioxide would either accumulate until oceans boil or vanish until the planet freezes. The timing of continental growth and the dance of plates set the pace of this regulation, and also distribute nutrients by grinding rock to dust, and by raising land that streams carry to the sea, where life turns dissolved elements into shells that eventually become limestone and dolomite. Above the crust, a magnetic field guards the atmosphere. In the molten outer core, iron-rich fluid convects and moves under the push of heat from deeper layers and the pull of rotation, creating a dynamo that generates a magnetic field. This field deflects charged particles from the sun and from the galaxy, reducing atmospheric erosion and modulating the chemistry of the upper air. Evidence from ancient lavas shows that Earth's field switches polarity many times, but the strength persists across aeons, and this persistence helps keep the atmosphere and water stable. Planets of similar size without a dynamo reveal the difference. Without a global field, upper air is stripped more efficiently, especially when the host star is young and active. Earth's star changes too, but slowly. The sun brightens over billions of years as helium accumulates in its core, yet the thermostat of weathering and the partitioning of gases between rocks, oceans, and air keep surface temperatures within a band where liquid water and complex chemistry persist. The faint young sun paradox, the puzzle of how early Earth stays wet under a dimmer star, finds relief in higher greenhouse gas levels, in lower land fractions that reduce weathering sinks, and perhaps in fewer bright clouds, though the details remain debated. Later, as the sun brightens, the silicate weathering cycle has more leverage and can draw down carbon dioxide. Terrestrial plants evolving much later deepen this draw by breaking rock with roots and by building soils that speed chemical reactions. The ocean also acts as a buffer, storing heat and carbon and redistributing warmth from equator to poles. Even with these stabilizers, the planet suffers shocks. Giant impacts early on reshape the surface, and one dramatic collision likely births the Moon, whose tidal pull slows Earth's rotation and stabilizes its axial tilt. A steady tilt limits extreme swings in climate and helps the seasons settle into patterns that life can exploit. Over long spans, the tilt still wanders, and the shape of Earth's orbit shifts. These cycles modulate sunlight, nudging ice sheets to grow and retreat. The resulting cold and warm intervals appear in layered sediments, in bubbles of ancient air, trapped in ice, and in fossils that trace life's responses as species move, adapt, or vanish. Catastrophes arrive from within as well. Flood basalts pour across continents in episodes that release volcanic gases and aerosols on scales that strain the thermostat. Mass extinctions coincide with such outpourings and with asteroid strikes, but recovery follows as the carbon cycle works and habitats reopen. The record shows resilience and fragility at once, long stability punctuated by rare, sharp breaks. Life does not simply endure these changes, it participates in the balance. Photosynthesis draws carbon dioxide from air and water, and vents oxygen, which reacts with iron and sulfur and eventually fills the sky, allowing an ozone layer to form that shields the surface from harsh ultraviolet light. The rise of oxygen changes mineralogy, climate, and the energetics of metabolism, enabling larger and more active organisms. Methane, a potent greenhouse gas, falls as oxygen grows, cooling the planet unless other gases compensate. The coevolution of life and environment feeds back into tectonics, as sediments rich in organics subduct and alter the mantle's oxidation state, and into climate as forests darken land, changing how much sunlight the planet reflects. In this web of causes and effects, near misses proliferate. Slightly more volcanic outgassing could overwhelm weathering. Slightly less could plunge the planet into a snowball state, where oceans freeze to low latitudes. Measurements from ancient deposits point to episodes when ice reached the tropics. Volcanoes under ice and a halt to weathering then allowed carbon dioxide to accumulate until a greenhouse pulse melted the shell, a violent thaw, recorded by cap carbonates that blanket the world after the freeze. The system bends and rebounds, and the rebound proves as important as the shock. The solar system itself provides hazards and aids. Giant planets patrol the outskirts and scatter comets. Their resonances stir belts of debris, sometimes increasing the rate of impacts, sometimes reducing it by clearing or deflecting projectiles. Over very long times, the shape and tilt of orbits evolve. Jupiter's gravity tugs at Earth's path and influences climate cycles in subtle ways. The Moon slows spin and dampens wobble. The Sun's activity cycles vary the stream of charged particles and the modulation of cosmic rays, which may influence cloud seeds in small ways. Each effect is minor compared with a basic energy budget, but the accumulation of many minor effects can help push a marginal climate into a new state. Against this backdrop, the emergence and persistence of liquid water on the surface stand out as a defining feature. Water shapes crust by lubricating the deep interface where plates dive, and by lowering the melting point of rocks, thus facilitating subduction and volcanism. Without sufficient water, plates might lock and the conveyor would stall, ending the long-term carbon cycle. Conversely, with too much surface water and little land weathering might not keep up with volcanic supply, leaving a hot and cloudy world. The distribution of continents matters because mountain building increases weathering rates, and the placement of land around poles influences ice albedo feedbacks. Ocean circulation redistributes heat, and openings and closings of seaways can rearrange climate dramatically. The responses of the biosphere to these rearrangements add further texture as grasslands expand or forests retreat, and the planet's surface reflectivity shifts. Many habitability factors therefore entwine. A planet's mass sets gravity and atmospheric retention. Its initial inventory of volatile elements acquired from the disk and from impact set starting conditions. The presence of a large satellite shapes spin and tides. A position within a band where starlight allows liquid water on the surface is necessary but not sufficient. Interior heat tectonics, magnetic shielding, and the choreography of a planetary system together must write a long-running equilibrium with room for variation and recovery. The very fact that such a balance is held through multiple extinctions and upheavals demonstrates that stability does not mean stillness. Stability means a capacity to absorb, to reroute, and to reset. This view keeps Earth within the chain of earlier chapters. The possibility that something rises from almost nothing relies on structures that deliver energy in measured ways, and on systems that buffer that energy. Earth's history shows how a planet can act as a governor, converting internal heat and stellar light into cycles that maintain ranges, where oceans do not boil or freeze solid, where gases keep to partial pressures that allow breathing and weather, and where chemistry can proceed for billions of years. The open questions bind this chapter to the future. How narrowly tuned is plate tectonics to a planet-size composition and water content? How often do dynamos survive for billions of years? How strongly do giant planet architectures influence impact rates and climate stability? The catalogue of exoplanets begins to answer by offering comparisons super-Earths with thick air-bare rocks close to harsh stars, ocean worlds beyond snowlines, and temperate planets in wide orbits around calm suns, spectra that reveal water vapor and carbon dioxide in alien skies, test whether the ingredients of balance repeat elsewhere, and patches of infrared light that hint at continents and oceans test the presence of cycles that grind and recycle. Even if Earth is one outcome among many, the arc of its balance clarifies a principle long habitability works, like a braid of feedbacks, physical and biological, that tie a planet to ranges where liquid water and energy flows sustain complexity. The balance is contingent, not fated, yet it is resilient. And because it is resilient, it becomes a path by which matter remembers and anticipates, a path by which an old star and a restless mantle together keep a surface, clement long enough for awareness to rise and ask how everything began. Conscious matter begins as a flow of energy through chemistry, and the wonder is not that atoms can think, but that the conditions for persistence naturally favor patterns that predict. A planet with long, stable ranges of temperature and liquid water offers niches where molecules that store instructions can copy with occasional errors. Selection keeps those that build robust bodies and reliable metabolisms. Over time, nervous systems emerge as adaptive organs that compress the torrent of sensation into useful summaries. A simple nerve cell fires or rests a kind of biological switch coupled to a membrane pump that trades energy for order. Networks of such cells implement feedback signals, reinforce paths that succeed and fade along paths that fail. In this way, information becomes a physical currency as concrete as heat or momentum. Organisms that harvest gradients more skillfully leave more descendants, and the skill often depends on learning to predict the next moment from the present one. Memory carries those predictions forward. Incessant change in the environment ensures that fixed rules alone cannot suffice. Plasticity, the capacity to rewire, becomes a trait that evolution amplifies. Eyes evolve to sample light, ears to sample pressure waves, taste and smell, to sample molecules, skin and whiskers to sample touch and motion. Multiplying sensors alone would flood the system unless there is a means to compress, and brains are compression engines preserving essential relations while discarding noise. The cortex of a mammal grows into layered sheets, where columns of cells tune themselves to edges, tones, textures, and timing. Deep structures compete and cooperate to tag events with valence and to route energy toward action. Electrochemical pulses propagate along axons, cross synapses filled with molecules and open channels in their targets. The machinery is messy and slow compared with electronic devices, yet it excels at parallel evaluation and graceful degradation. Because learning imposes structure, the machine becomes a map of the regularities it encounters. A bird that navigates by stars and magnetic fields encodes celestial rotation and field geometry in circuits. A cephalopod that swaps color and texture across its skin in a heartbeat models the statistics of reef and sand. A primate that strings sounds into grammar internalizes probabilities of word order and meaning. In all these cases, prediction saves energy because responses prepare before shocks arrive, and spare muscles do not waste effort on unlikely moves. Thermodynamics lies beneath. To maintain low internal entropy, a living system must export waste heat and disorder to its surroundings. That export is cheaper if perception and action are tuned because the system can steer into favorable gradients rather than fight them. This is not metaphor, it is a ledger. Organisms with accurate internal models spend less energy correcting mistakes. Conscious experience in this picture is not an ingredient poured into matter, but a process that rides on many coordinated loops, integrating diverse signals into a single scene that the body treats as real enough to act upon. The unity of experience reflects the need to commit to one coherent plan at a time. The richness of detail reflects the cost of missing rare but dangerous events. Sleep appears as maintenance, a period when replay consolidates memory. Synapses renormalize and waste metabolites clear. Dreams rehearse and recombine a search over possible future causes and responses that may aid prediction when morning returns. The step from complex reaction to awareness remains hard to define, yet certain signatures suggest a threshold. When many distant brain regions synchronize their rhythms while still holding distinct content, global integration is working. When signals remain local and uncoordinated scenes fragment. Surgical electrical stimulation and gentle magnetic pulses show that changing activity in one hub can alter perception across the field, a sign that hubs broker unity. Conditions that break integration, such as deep anesthesia or certain seizures, drop the lights even though some circuits still grind. These observations do not define consciousness in final terms, but they ground it in causal architecture rather than in mystery alone. The body and environment co-author the mind. Heartbeats, breathing, stomach waves, and the tug of muscles feed the brain with rhythms that serve as clocks for coordinating many loops. The world delivers regularities at many scales, from day and night to seasons to social signals. Brains entrain to these rhythms, laying down expectations that reduce surprise. Surprise is not merely a feeling, it is a measure of model mismatch. High surprise forces revision and costs metabolic energy. Low surprise indicates that control is working and that the internal model remains apt. The hunger for patterns that reduce surprise explains why agents seek information even when doing so offers no immediate food or shelter. Curiosity is a strategy to mine future energy savings by learning better models today. Language takes the compression further. Patterns that began as gestures and calls become arbitrary symbols that stand for objects, actions, and relations. Symbols can be recombined to describe scenes never seen and futures not yet real. A storyteller transmits a model across nervous systems, aligning expectations and therefore actions in groups. Culture becomes a memory that outlasts individuals, a way to store compressed knowledge externally in marks and tools. Writing, art, and mathematics extend the loop of prediction beyond the lone brain into a network where shared models steer the behavior of many. Technology amplifies the effect until a species can change the planet that once only changed it. Tools that record and compute alter the energy landscape by making new paths cheap. The risk grows with power. If the model is wrong, errors scale. Awareness must then include awareness of limits. Science. The ritual of organized doubt arises as a cultural response to the ease of self-deception. Instruments replace senses where bias is strong. Statistics replace anecdotes where noise is thick. Agencies build telescopes and microscopes that extend perception to the cosmic and the cellular. Laboratories codify ways to separate signal from wish. The same principles that reveal the ancient afterglow reveal neural currents. The same discipline that maps galaxies maps brain networks. A mirror appears, the cosmos learns about itself through patterns encoded in small parts of its matter. This thought can sound like a flourish, yet it is simply a consequence of recursion, a system with subsystems that model the whole will, in time model the act of modeling. Ethics can be read as a thermodynamic and informational strategy as well. Cooperation stabilizes groups, reduces wasted conflict, and shares models that would be too expensive for one mind to compute alone. The line from nothing to awareness thus passes through many filters. Fields fluctuate and seed a web. Gas collapses and forges stars that build heavy elements. Disks form planets that keep energy flowing. Chemistry learns to copy. Bodies learn to sense and move. Brains learn to predict and compress. Symbols allow collective memory. None of these steps appears inevitable in detail, yet each builds on prior gradients and structures, so that what seems wildly improbable at once becomes more likely given the specific past. Awareness does not float. It perches on an edifice of self-correcting models fueled by energy captured from the environment. That perch remains precarious. Brains tire and fail. Cultures ossify. Models drift out of date while the world changes underfoot. The practical lesson that folds back into the cosmic question is humility. Any account of how everything starts from almost nothing must admit that understanding is itself a physical state stored in fragile arrangements that require care. The mystery persists because each gain in prediction exposes a larger boundary of unknowns, yet the progress matters. It allows a species to look backward across billions of years and forward across generations to trace how an old star and a cooling planet make room for minds, and to feel the weight of that room as a responsibility to keep gradients gentle, diversity wide, and stories honest. In this light, consciousness is not an exception to nature but a refinement of it, the point where matter behaves in ways that preserve and propagate accurate models of its future. The most intricate patterns arise where energy can be managed and awareness is management in its most flexible form. The cosmos writes its own autobiography through nervous tissue, and the writing both clarifies and deepens the question that began this journey. Origins replay across other skies as a test of whether the path from fluctuation to observer is a rare accident or a common refrain. The search begins with worlds that dim their stars. Space telescopes measure tiny dips in starlight as planets pass in front, and careful timing reveals sizes, orbits, and seasons. The Kepler mission turns a star field into a census and shows that small rocky planets are common, including many in the temperate band where liquid water could exist on a surface. The transiting exoplanet survey satellite swings its gaze across bright nearby stars so that telescopes on and above Earth can probe their worlds further. With the James Webb Space Telescope spectrograph spread the faint light from planetary atmospheres into bands where water vapor, carbon dioxide, methane, and other molecules leave fingerprints. Each detection is a weather report for an alien sky. The path from gas to inference is careful. Clouds mute signals, star spots mimic them, and instrumental quirks leave echoes. Yet bit by bit the list of molecules grows, including carbon-bearing compounds that speak to chemistry rather than to life itself. The next step asks not just what is present, but what combinations are hard to make without biological fluxes. On Earth, oxygen joined to nitrogen in the air, carbon dioxide in the sky, above oceans, and methane from wetlands and guts interact in non-equilibrium ways that steady geologic processes seldom maintain. A distant observer might read those gases together as a hint of metabolism. That thought guides present surveys. Models simulate how volcanoes' water loss and rock reactions could paint false positives, and observers target stars calm enough that flares do not strip air or flood spectra with noise, because low-mass stars can be both friendly in number and hostile in activity. On a handful of promising worlds, retrievals of atmospheric composition already test scenarios where photochemistry and geology alone struggle to reproduce the data. The ground joins the effort. The European Southern Observatory's Very Large Telescope, and before long the Extremely Large Telescope, along with other giants, sharpen the view with adaptive optics and high-resolution spectrographs that can separate a planet's faint spectrum from the glare of its star. When a planet swings around its sun, its spectral lines shift slightly from motion. By following that shift, astronomers extract the planet's signal and compare it to models of reflected light from oceans, deserts, and clouds. In principle, a glint at crescent phase could betray calm seas, and subtle colour patterns over a rotation could hint at patchy continents and weather fronts. Even a coarse measure of day and night temperature could distinguish between thick air that spreads heat and bare rock that bakes and freezes. One day imaging a pale point and watching its spectrum through a full year may reveal a breathing season carbon dioxide falling as plant analogues grow and rising as they sleep. That dream does not require romanticizing life. It requires only acknowledging that living systems move gases in bulk. Oceans on distant worlds may also speak. A planet with a deep global ocean could lack plate tectonics and carbon cycling, leaving a different trajectory for climate and biosignatures. Some moons around giant planets in cool orbits might carry subsurface oceans warmed by tides, their signs hidden unless fountains breach the ice as on Enceladus. Even there, telescopes could read the composition of plumes against a bright planet if geometry and patience align. The replay of origins therefore depends on architectures: star-type planet mass, orbit shape satellite companions, and the history of impacts and migration. Catalogues already show that architectures differ wildly from the solar system. There are compact strings of small worlds huddled close to their suns, young systems with wide rings, where planets clear lanes and hot giants that hug so near that metals rain. This diversity clarifies that Earth is one script among many. Some scripts may be friendlier with lasting gentle light and quiet magnetized winds from small, slowly rotating stars. Others may be forbidding with flares that strip air and sterilize. The measure will be statistical. If biosignature pairs and trios appear in many skies around many types of suns, the inference tilts toward commonality. If the search returns only sterile equilibria and volcanic skies, rarity grows. A separate line of evidence listens for intention. Radio telescopes tune to quiet bands where the galaxy itself is sparse in noise, and they sift for narrow signals that do not match nature's broad lines. Optical instruments hunt for ultra-short laser flashes that no star produces. Infrared surveys look for waste heat from large engineered structures that could glimmer as excess at mid-wavelengths. Planetary atmospheres could betray industry if molecules such as chlorofluorocarbons or nitrogen oxides appear without plausible geologic flows. Night-side illumination on a tidally locked world might flicker in ways that clouds cannot explain. Each techno-signature proposal has benign counterfeits, from dust pulsations or instrument ghosts, so teams build protocols of confirmation and independent replication. The aim is not spectacle, but rigor, because a single false positive can waste years. So far, these searches have found only mysteries that collapse into natural causes when inspected closely. Even so, the null results teach. They bound the number of loud transmitters and favour futures where any long-lived society either keeps its beacons quiet or radiates softly. The lack of obvious megastructures suggests that engineering most often stays local, or that mature strategies favour efficiency that hides heat. The silence is not an answer, but it is a contour on the map. The risk of self-deception, already high in geochemical biosignatures, climbs further with technosignatures. For this reason, the same discipline that made the ancient afterglow into a number repeats here: blind analyses, open data where possible, and cross-checks by independent teams using different telescopes and methods. New instruments will expand the reach. The Nancy Grace Roman Space Telescope will open a wide view for direct imaging and microlensing, catching planets far from their suns and measuring masses and orbits without transits. Ground arrays will push high dispersion chronography to separate a tiny planetary line from the blaze of a sun by exploiting the Doppler dance. Future large space telescopes designed to block starlight with starshades or internal masks could dissect Earth-sized worlds around nearby calm stars, pixel by pixel and season by season. Meanwhile, planet finders continue to grow the sample toward the thousands of temperate rocky targets that make ensembles powerful. The replay of origins also runs backward from signs to processes. If a planet shows oxygen and methane together, models must predict the required surface fluxes and check whether volcanoes impacts photolysis, and water loss can fake the signal. If haze dominates the sky, the absorption might hide life below, or it might mark chemistry that never climbs to cells. Hills and valleys in the spectrum must be weighed against clouds that mute them. Surface features implied by glint or colour must be tested against light curves from worlds with known ocean fractions to avoid wishful mapping. The ambition is to make every inference a contest between life and lifelessness, and to let the data choose. Across the search, humility and boldness share the same seat. Humility because the number of ways to be fooled is large, and history is full of mirages. Boldness because the instruments now in hand and soon in flight can overturn priors rapidly. Already the lesson that small rocky planets are abundant changes the baseline odds. Already the detection of water vapor and carbon dioxide on worlds baked by their suns proves that nature writes familiar chemistry under foreign light. The next decisive steps will come from pairing molecules in combinations that ask for metabolism from phase curves that show heat moving as if winds cross continents and seas, from time series that breathe, and perhaps from a whisper in the radio or an unnatural blink of light that repeats with intent. If echoes of origin appear often, then something from almost nothing is not a singular event, but a pattern that the universe tends to draw when the canvas and palette align. If echoes remain rare, their rarity becomes its own instruction, telling that long balances like Earth's seldom hold. Either outcome illuminates the path already walked. In both cases, the search itself is a continuation of the story, a species using symbols and metal mirrors to ask whether it is typical or strange. The answer, partial and provisional, will thread back to the beginning by clarifying which rules are general, which accidents were essential, and how often the bridge from field fluctuations to living maps spans the gap. The edges of explanation gather where evidence thins and models reach beyond familiar anchors, yet even here the path remains empirical, because each bold idea must leave a trace that telescopes or laboratories can seek. The first edge concerns initial conditions. Observations point to a beginning that is astonishingly smooth and nearly flat, with tiny irregularities of the right amplitude to grow into structure. The early sprint of expansion explains how such conditions could arise from a wider range of starting points, but it still invites the question of why there was a field high on a plateau and why it relaxed as it did. Some frameworks suggest that what we call the beginning is a patch within a larger quilt where quantum fluctuations make regions that inflate while others do not. In such a landscape, physical constants and particle content vary from place to place, and observers appear only where long-lived stars and stable chemistry are permitted. This multiverse picture trades a single answer for a distribution, and moves the burden to statistics. If our values are typical among the zones that allow observers, then the coincidence of a tiny vacuum energy and a nearly flat geometry becomes less strange. Yet typicality is a fragile word, and the approach draws criticism because direct tests seem remote. Even here there are proposed scars to seek. If neighbouring inflating regions ever collide with ours, they might emboss the ancient afterglow with a subtle asymmetry, a azimuthal bruise that dedicated analyses have searched for and not found decisively. If the sprint involved more than one field-faint non-Gaussian fingerprints, could appear in patterns of the sky. Maps from space missions have pushed those fingerprints to very low levels, sharpening the sieve through which theory must pass. Another edge questions whether time itself is fundamental. In some quantum cosmology sketches, the whole is described by a timeless rule, and time emerges as a relational property when parts of the system are treated as clocks for other parts. In this view, the origin is not a moment in a prior time, but a state from which time arises with the growth of correlations. The arrow that points from past to future would then trace the growth of entropy and of recorded structure, not a built-in preference of time itself. The cosmos gains a memory as structures freeze, and that memory gives direction. This story does not yet predict numbers that observers can weigh, but it suggests why low-entropy initial conditions matter only from such a beginning. Can information channels open wide enough for galaxies, planets, and minds? A different route imagines that contraction precedes expansion, either in a single bounce or in an endless cycle. In a bounce, the universe shrinks to a high but finite density set by new physics, then rebounds into growth. In cycles, each expansion ends in thinning and cooling, that later reverses into collapse with the subsequent bounce erasing most, but not all memory. These pictures address the discomfort of an origin from an instantaneous singularity, and they concede ripples in ways that mimic a sprint. They also face sharp constraints from the ancient afterglow, which shows a remarkably clean blueprint that is difficult to carry through a violent rebirth without leaving marks. Some versions predict specific departures in the pattern of temperature and polarization, or oscillatory features in the distribution of galaxies. Searches have not confirmed such signatures, but bounds continue to improve. A quieter edge lives in the odd arithmetic of vacuum energy. The smallest estimate from quantum fields overshoots the observed value by a ridiculous factor, a chasm that mocks our understanding. Perhaps an unknown symmetry cancels contributions to nearly zero. Perhaps a dynamical relaxation drives the value downward over cosmic time. Perhaps many regions have many values and only small ones host observers. Each option has links to observation. A gentle evolution of the push would bend the history of distances and growth by a trace that next-generation surveys can pursue. A symmetry might predict new particles or relations that colliders or rare decay experiments could find. A landscape might predict statistical relations among other constants that exoplanet demographics and nuclear physics could test indirectly. The puzzle of why matter survived over antimatter draws another line. The early fireball appears to carry a tiny preference for matter, a surplus of a few parts in a billion without which stars and planets would not exist. Laboratories have measured modest asymmetries in the decays of short-lived particles that show how the laws themselves distinguish between time directions in subtle ways, but the measured effects seem too small to produce the cosmic surplus. Ideas that tie the asymmetry to neutrinos to heavy decays just after the sprint, or to new fields coupled to the expansion, write predictions for rare processes and for the neutrino's own character that underground detectors, reactor experiments and observatories follow. If neutrinos are their own antiparticles, a very rare nuclear process would occur with no outgoing neutrinos at all. Searches continue with crystals and noble liquids for a whisper that has not yet been heard. Meanwhile, gravitational wave observatories under the National Science Foundation and partner agencies listen to space itself for clues to the early rulebook. The current network has already turned the sky into an audio map of compact object mergers, but its deepest promise for origins sits at lower frequencies and higher redshifts, where a background from the earliest moments might hum. Planned space-based detectors could hear the chorus from binary black holes across cosmic time, and perhaps catch relics of phase changes in the infant universe if those changes shook space-time strongly. If the early sprint reached very high energies, it might have left a background too faint for present ears. If it ran more gently, as current limits suggest, the background may remain inaudible, a constraint that still narrows the models. A different class of edges asks whether the laws we write are complete on the spans we claim. Gravity has passed all tests in the solar system and in binary pulsars. On galactic and larger scales, its predictions succeed when unseen matter is added, but modest tensions in the measured rate of structure growth and in the local expansion speed invite caution. It could be that small systematics contaminate one or both roots to those numbers. It could be that new components such as early dark energy or light relics, a shade warmer than expected, tweak the ledger. It could be that gravity itself softens very gently over long distances. The way voids empty, the way clusters grow, and the way galaxies fall together across billions of light years will sharpen this choice as ongoing sky surveys mature. Even as ideas multiply, a shared ethic holds an explanation must become a program of measurements or it is a poem. The agencies and collaborations that turned faint static into the first map and that traced the web through billions of galaxies now design instruments to test the newest whispers. The habit that guarded the ancient afterglow against dust and noise now guards the search for faint polarizations, subtle lensing, and tiny departures from a constant push. The discipline of blind analyses and independent replication remains the vaccine against wish. In this discipline, a final edge appears, the one that acknowledges that the question of why there is anything rather than nothing may not have an answer of the kind that earlier chapters offered. It may remain an open horizon that recedes as clarity grows. This is not a failure. It is an orientation that prevents premature closure. The cosmos has yielded a chain of causes from field fluctuations to galaxies, from disks to planets, from chemistry to awareness. At each link the world proved more legible than expected, and at each link the next question grew sharper. If the answer to the deepest, why, remains elusive, the how has become a rich landscape where predictions meet sky and stone. The story therefore ends without ending, with a network of instruments listening and looking, with models that dare more while promising to be broken, with a species that has turned starlight into a mirror. Something rose from almost nothing, and the traces of that rise are written in the cold afterglow, in the spider web of galaxies, in the chemistry of stones, and in the nervous electricity that asks again how the first lines were drawn.